we'll kind of just ease our way in through this. We talked about electronegativity, right? Okay, and then I believe what we had time for is I skipped a whole crap ton of slides and jumped to the end for like the summary slide. Okay, and that was really, really last minute. Let's go back and do that again. I'll help you with that in just a second, Jonathan. This slide, right? You guys remember this? And I think everybody was in the process of packing up at the time, which I don't blame you because I was talking a lot. The exam is next Thursday. There is a significant amount of content that you need to have memorized or at least have accessible. Okay? Some of that stuff you can memorize for the whole exam or attempt to memorize for the whole exam. I would argue that there's other things like the atomic radius, like ionization energy, like electronegativity, okay? Like valence electrons. That information is stored on the periodic table. If you can generate some kind of notes for yourself, so as soon as you get the test and then write that information down, you no longer have to keep it for the whole test. And when you move through the test, when you see a question on atomic radius, all you've got to do is look at those notes that you just wrote. Does that make sense? Okay. To test-taking strategies, this is something that everybody tends to freak out at when it comes to tests, sometimes in chemistry, sometimes in other fields. The intent of a test is to not make you feel good. Right? And for whatever reason, it seems like in a lot of cases, at least within the state of Arizona, everybody takes tests to go like, oh, I feel better because I know everything. No test should ever be written like that. That's not the point of a test. A test is to find out what you don't know, right? Which is an entirely different mindset because you start to shut down because you start to find things that you don't know, right? That is why you should never take a test in sequence, right? Starting with question 1 and moving through to the next question, because you may very well find that you know the last answer or the last question, but you don't know the first one. If you go through in sequence, what happens? Get to the last question and you get it all wrong. Right? So when you go through and take the test for next Thursday, what you should be trying to do is find the questions that you know. Right? Spend the time to get those right. Don't spend time on your weaknesses, right? At least not at first. They were weak, you were probably going to get them wrong. Put answers down for your strengths first. You can double back and work on your weaknesses during the test. Does that make sense? Okay. Some of that has to do with ways that you can cognitively download as much information as possible. Putting down trends can help out. If you've got other random notes that you're like, I'm pretty sure I'm going to forget this, you should write that down pretty quickly into the exam too. Okay. A lot of people, well, it's not that hard to memorize the trend. Okay. It isn't that hard to memorize the trend for a minute, 2 minutes, 5 minutes. Okay? Particularly when that's all you're thinking about. But on a test, what are you going to encounter? Probably 39 other questions that aren't on that content and are going to make you forget that trend. So that when you then get to the question, you get it backwards. Okay? So try to kind of do a data dump, if you will, of the major stuff you've got memorized and put it on the first page. Right? You can now always reference that as you move through the exam. Right? This is something that works for every single class. Right? You shouldn't be trying to memorize all the content unless you're forced to only click answer choices, right? Which will happen in the future.
An estimated amount, how many questions are there?
You're looking at about 40 questions, maybe 45.
So you need scantrons.
I will provide you a Scantron. I do not like it when you buy Scantrons and everybody buys a different frickin' Scantron and then they don't run through the machine and I have to create it by hand. Okay. Yeah, it's irritating. So it is not completely multiple choice. We've got 4 to 5 short answer questions and then the rest would be multiple choice. There will be some questions on the English content. Right? When I'm in class, guess what I'm doing? I'm taking notes. Why is that helpful? Now Greg can go back and be like, oh, what notes did you have, Mike? Oh, not only do I think that was important, but you also thought it was important because you wrote it down in your notes. Let's make a test question. Ta-da! Right? It is a learning community. You are expected to know both aspects, or be picking up both aspects of the class. Okay? Other questions? Okay. So we'll backtrack through a bunch of these, start talking about some kind of general concept topic stuff first. We then jump kind of into chapter 12. Chapter 12 talks about bonds. And when I bring atoms together, they can potentially form a bond. Okay. Chapter 12 uses a very kind of horrible way to differentiate those bond types. Okay. If I bring two atoms near each other, first and foremost, what's the first thing those two atoms are going to see of each other? The electrons. Why the electrons?
Because
They're on the outside. So they're going to see all of the electrons on the outside? No. What electrons are they going to see? The highest energy electrons, okay, which means weakest connection to the atom. Okay, those would be the ones furthest out, so highest energy level, which would be our valence electrons. Okay, so you need to be able to identify the valence electrons. We talked about that, right? We look at the column name at the top of the periodic table. Yeah? That gets us our valence electrons for everything underneath that column. Okay? Before we get into applying those electrons, the two categories that come out look at how those electrons were distributed between the two molecules. If the two atoms, as I bring them together, just steal electrons, one atom sees that the outermost electrons of the other one and takes them away. Okay? This is now a complete transfer of electrons from one atom to another. Okay? We're looking at an ionic bond. Okay? Why would we get a complete transfer of electrons from one atom to another? What's stronger? Yeah.
The positive energy.
Not positive energy, and it's not looking at our protons either. There's a fancy word for it. Big, long one. The electronegativity. So when we get a large difference in electronegativity, one atom is ripping the electrons away from the other atom. So one has a very high electronegativity and one has a very low electronegativity. As a general rule, that tends to happen between metals and nonmetals. Metals all have very low electronegativities. Nonmetals have very high electronegativities. So anytime I bring them near each other, I tend to generate an ionic bond. Note I am saying tend, because this isn't a black and white system, okay? At least officially. We're going to start here calling it black and white. If they're now two nonmetals, I get covalent bonds. What if I have two metals? Because that pattern's not on here, right? I got metal, nonmetal, and then two nonmetals. What if I have two metals? It's called a metallic bond. Okay? And a metallic bond we aren't going to study this semester, so don't stress about it. Okay? So we get our two primary categories right now, ionic and covalent. Are those all consistent? All right, let's take a look at the covalent bonds. H2O, hydrogen, metal or nonmetal? It's a nonmetal. Remember, it's tricky in its placement on the periodic table. Oxygen, metal, nonmetal? Nonmetal. So we have a covalent bond. Hydrogen, nonmetal, chlorine, nonmetal. So covalent bond. One of the things that's useful about looking at our bonds is it can help us predict something about their reactivity, okay, or their charge states. So water or H2O and HCl both have the same type of bond. So we might say, well, they're going to react the same way because they have the same type of internal structure. Okay? H2O is water. HCl is hydrogen chloride, also known as hydrochloric acid. We'll deal with the names of those later in this semester. Okay? Water and hydrochloric acid. Okay? Are they really the same? No. Why not? You could drink one, and if you drank the other one, you would die very swiftly and painfully. Right? Those are pretty big differences. Right? Some of their chemistry can be predicted based off of the internal bond structure, but not all of it. So we have to be a little bit careful by just jumping to assumptions there. Within our ionic bonds, we're really looking at positive charges, right, being our metals. Because positive charge is too long of a phrase, we invent a new term, and we call them cations. Okay? Why do we call them cations? This is horrible. It's pretty close. Because cats are positive. Not me. Okay. Cations are positive. Those are typically our metals. Not guaranteed, but those are typically our metals. The negative charge ones are our anions. They're nonmetals. Because I got nothing for that one. That just is. Okay? Yes? Typically. Okay. At this stage, remember, we're looking at ionic and covalent as black and white. So they're absolutes right now. Okay? Probably within 2 weeks, we'll change our minds on that. Okay? One of the things that's nice is because ionic compounds are very, very regular. They have a complete transfer of electrons across. Everything is perfectly kind of symmetric and smooth, and we can compare these out as spheres. Okay? Which then means we get very regular crystalline solids. Okay? So we would get the picture here, which is a nice cube of all these little circles around each other. Okay? So we can treat them almost like unique marbles. Okay? Which brings up a fun thing with ionic radius. If I take a look at a sodium atom and compare that to a chlorine atom. Take a look at the periodic table. Sodium, what is that? Row 3, group 1. Everybody found it? Find chlorine, row 3, or period 3, and group 7 or 17. I accept both. Okay. They're in the same period. What should happen to the radius? It should decrease. Why does it decrease? What was that? Proton pull. So potassium should be smaller than sodium because potassium has more protons? No. Okay, so I don't accept your answer fully. Why does it decrease when we go sodium to chlorine?
The electron configuration.
Kind of. It's due to our outermost electrons, and our outermost electrons, when we move from sodium to chlorine or within any period, go to the same energy level, which means they're the same distance from the nucleus. That, in conjunction with the fact that we have a stronger nucleus, is what draws those electrons in. That's why when we look at the size, the sodium atom is significantly larger than the chlorine atom. Right? If we now bring them together to make a bond, chlorine, really, really high electronegativity. Sodium, really, 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 really low. What does that mean? Okay. That last highest valence electron for sodium, it doesn't really want it. It's not really holding on to it. Chlorine, because it has such a high electronegativity, grabs that electron. Okay. By grabbing it, it attracts it to itself. That electron now belongs solely to the chlorine. What does that do to the radius of both of those elements? They change. Good. Sodium atom. What should it become? So number one, it lost an electron, so it should become a cation or positive. Okay. What should its size be? Should I be drawing it bigger? No, why not? It lost an electron, which means by definition it has to be getting smaller. So it turns out it does get smaller. What happens to the chlorine atom?
That also gets smaller.
It gained an electron, so it's an anion. It is now negatively charged. What happens to its radius? It gets bigger. Do I have to worry about the size of the nucleus in this case? No, why not? The nucleus isn't changing. We're just saying, am I adding extra electrons or am I removing electrons? That's it. There's no nuclear effect now. It's literally just the amount of electrons. And sure enough, this is exactly what we see. The chlorine atom, or chloride ion, gets significantly larger when it accepts an electron. The sodium gets significantly smaller. Okay? Which brings in an interesting point. When I went through and said the negative chlorine, what did I call it? I know it just happened really fast.
Chloride?
I said chloride. What was this one that was just Cl atom? Chlorine. Is it the same name? No, why not? One is negatively charged. The name allows me to know that it has picked up a charge, and in particular a negative charge. What happened with this other one? The sodium atom became the positive one. What did I call it? I still called it sodium. Okay? And this is one of the things that can become confusing. Because when we talk to people out in the real world and we say, well, certain things are dangerous, okay? Sodium. Do you need sodium to live? Yes, that's how your muscles function. But if I ingest a chunk of sodium, what happens? I die, rather horrifically and probably an explosion. Okay? But I need sodium to live. I need sodium ion to live. Sodium metal is dangerous. Sodium ion, in limited quantities, isn't that big a deal. Okay? That's how my muscles function. So when we talk with people outside, we have to recognize that sometimes our nomenclature is now, our naming systems aren't super clear in what's happening. In this case, we are changing the electronic environment, and that change in the electronic environment drastically changes its chemical interactivity. Going from exploding my head to allowing me to live. Okay? It's a pretty huge difference. Okay? Same kind of thing happens with chlorine. Chlorine atom, if we actually turned it into a molecule, chlorine molecule, is toxic. It was used in the World War II, I believe, as mustard gas to kill people. Chloride ion is an important electrolyte. Okay? It really isn't that big a deal. Okay? So we have to be kind of careful about what those charge states are. They make a really big difference in the chemistry of our molecules. Okay? We've got a